The next one we have here is a river delta. When streams or rivers empty into a larger body of water, they can create a delta. When they do, they slow down and deposit their load. Remember, the load is the sediment and suspended particles that are in the river as it flows. Frequently, this load is deposited in a fan-shaped pattern called a delta. Over time, the land will build up and can cause islands and channels to form as well. So one of the most famous deltas is the Mississippi River Delta, and you're seeing pictures of that here in a couple different ways.
The world is divided into two kinds of people, those with innie belly buttons and those with outies. Rivers also have innies and outies, not belly buttons but mouths. Where rivers flow into the sea, the land either pokes out or bends inward. But rivers don't have umbilical cords, so why do they have innies and outies? Well, coasts are the front lines between two opposing forces, land and water. In order for the ocean to invade the land, sea level either has to come up or the land has to sink down or be eroded away. And in order for the land to advance into the ocean, sea level either has to drop or the land has to build or be lifted up. Obviously, if sea level drops and then rises back again, there's no net gain on either side. But things get more complicated when a river joins the battle. For example, during the last ice age, sea levels fell by over 120 meters, and rivers cut deeper and deeper valleys to reach the falling seas. Then, about 18,000 years ago, warming temperatures began to melt the ice, and the now rising seas flooded river valleys around the world, creating giant estuaries and giving us the innie-riddled coastlines we have today. But when the steady landward march of the seas finally began to slow about 7,000 years ago, the coastlines around the mouths of some rivers began to gain back some ground. The key factor was the sediments that rivers drop as their currents slow at the entrance to the sea. Where the sediment supply was big enough and the ocean was calm enough, the dropped dirt piled up, eventually forming new land that both lengthened the river and divided it in two. Dirt would continue to drop out and build up at the mouths of both channels, splitting the river again and again and again, creating a new lobe of land advancing slowly into the sea. Thus, the world's great outie river mouths, the fertile deltas like the Nile and the Yangtze that have helped foster human civilization since its birth, all came into being at just about the same time. The same can't be said for all of the world's outie belly buttons. What can be said, though, is that innies and outies, for both rivers and people, are a small record of how we came to be.
And then a second video that discusses more detail on how that delta can change over time.
Since the beginning of human civilization, people have settled along rivers and on the fertile deltas created by them. The sediment carried and deposited by mighty rushing waters creates land rich in nutrients and ideal for crops and livestock. Where there are uninhibited rivers, there is new, rich land, and where such resources abound, there are people. The problem with people settling along rivers and deltas is that rivers inevitably flood. This is good for the land because sediment from the water is deposited on the previously dry earth and replenishes the soil. However, this flooding can destroy the human homes established there. Thus, we build levees around these river titans in an attempt to keep the lumbering giants at bay. Louisiana has two of these breathing rivers, the Mississippi and its distributary, the Atchafalaya. The Mississippi has made Louisiana an international port of trade and commerce, and both rivers have contributed to the lush habitat of Louisiana's people and animals. Many smaller rivers feed into the Mississippi, creating a vast watershed that drains nearly 40% of the continental United States, and all combine to bring the Mississippi and its delta to life. The long-term consequence of levees, however, is prevention of land formation. Rivers deposit sediment in one area over hundreds or thousands of years, until the accumulation is so great that the new topography of the land causes the river to change course and begin to deposit sediment somewhere new. When a river is prevented by levees from flooding or changing course, the sediment it carries cannot build up the land, and over time erosion begins to wear away the already existing earth. In the case of the Mississippi River, these levees also mean that all of the sediment carried by the river is dumped uselessly into the Gulf of Mexico and over the continental shelf, illustrated here. As a result, the land of Louisiana's coast is sinking and eroding at an alarming rate, and people's homes and livelihoods are again in jeopardy. Here is a simplistic depiction of how a delta unrestricted by levees is formed. This model represents a bird's foot delta, similar to the Mississippi. Here we see the sediment being churned up and carried by the rushing waters. As more and more sediment rides with the water, the sand, silt, and clay begins to build up along the banks and in certain parts of the river mouth until channels are formed. Finally, the sediment has piled up so much that the water has had to divert itself around the newly created islands, and we now have an emerging birdfoot delta. Now, vegetation begins to form on the newly created and nutrient-enriched land around the river and on top of the island. Before and after, natural land production is a slow process. This delta would have taken approximately 1,000 years to form.
So your example could be the Mississippi River Delta. A delta is created by deposition, the deposit of materials, the deposit of a stream's load as it slows down and moves into a larger body of water. Something very similar to a delta is something called an alluvial fan. It's a similar process that can happen when a river makes a deposit on land instead of into a large body of water. If this happens on a flat land, an alluvial fan forms, which is a fan-shaped deposit that forms on land instead of in a larger body of water. Alluvial fans are usually created as flowing water interacts with mountains or hills or steep walls of canyons. So those areas I pointed out in the Washington Canyon that kind of look like gravity erosion is an example of an alluvial fan. Streams carrying alluvium can be trickles of rainwater and fast-moving creeks, or powerful rivers, or even runoff from agricultural and industry. As a stream flows down a hill, it picks up sand and other particles, which is the load or the alluvium. And this creates our alluvial fan. So they look very similar to deltas, except they're forming on land more than in a larger body of water. So here's some examples.
An alluvial fan is a fan or cone-shaped deposit of sediment, and is usually picks up sand and particles to form the fan shape.
This topographic map shows multiple mountains behind the alluvial fan. They're mostly located in desert regions.
They're built as flowing water interacts with mountains, hills, or the steep walls of canyons.
These smaller particles are going to be at the top or the point of the alluvial fan, and the larger particles can flow further if there's a large rushing body of water. If it's a slow body of water, sometimes the larger particles are dropped out sooner.
They're mostly located in desert or mountainous regions. Fans are made up of debris. They also pick up sand and particles since alluvial fans are made up of debris.
This is our model of a topographic map of an alluvial fan. As you can see, it slopes down from the top.
So here are some other examples of alluvial fans. This is in Death Valley, California. It's actually the mouth of a dried up river. The river carried its sediment. As the river rushed into the wide valley, the sediment fanned out across the triangle-shaped area, creating this alluvial fan. The narrow point of an alluvial fan, so this area right here, is called the apex, while the wide end of this triangle shape is called the apron. This is in the mountains of Iraq. This is in a seasonal alluvial fan or a seasonal stream. So during the rainy season, this runs with water, but then during the dry season, everything dries up. That's why it's an alluvial fan. So you can see here how there's a lot of agriculture based upon this area. This is some alluvial fans can form underwater, and we call those the river deltas that we discussed earlier. Some alluvial fans are not triggered by water, but they can be triggered by an earthquake or a landslide, as you see here. A debris cone is a type of alluvial fan with a steep slope over thousands of years, rainwater rushing down the sides of a canyon, like this one here in Marble Canyon, or you may see these also in the Grand Canyon, or in that Washington Canyon, the Yakima River Canyon, created these debris cones. So let me point out to you one of these debris cones. This kind of cone shape right through here, the debris that you can see, these are those debris cones, which are types of alluvial fans. So you have a picture like this on your notes. It points out a lot of the different things that we just talked about during this lesson on stream, erosion, deposition, landforms. There are 3 areas for you to label. So A here is pointing to the canyon, B is pointing to the meander, and specifically the inside of the meander, and C is pointing down here to the delta. And what it's asking you to do is label whether they were created by erosion or deposition. So to go over these, the canyon is created by erosion. The inside of the meander is created by deposition because that is the slower area. The outside of the meander is created by erosion. And then the river delta is created by deposition, or the depositing of materials. So that will be the end of this section of notes for the erosion and deposition of streams and channels.